In this tutorial, we're going to go over some practice questions from stoichiometry. Okay, so make sure you have a notebook where to indicate some of the key things, a periodic table, and also a calculator by your side. So feel free to pause the video and make sure you have all of those things with you. Let's get started. Calculate the number of moles for 5 by 10 to the power 2, that is copper atoms. Okay, so how do you get to determine the number of moles? So we do understand that basically Avogadro's constant basically is going to give us what? Avogadro's constant, which is 6.022 by 10 to the power 23, easy. Any number of things that you're talking about per what? Per mole. So in this case, what are we talking about? We're talking about atoms. So I'll say it's atoms per mole. So now the question is asking us to determine the number of moles for that number of atoms. So how do we get to do that? So since we're interested in making more or determining the mole, we can use Avogadro's constant as what? As a reciprocal. So I'll write what we have, 5.00 by 10 to the power 2. Okay. So I don't know what was supposed to be the power 20. Okay. So what is supposed to be 10 to the power 20? So say those number of what? Atoms. So Avogadro's constant is going to be its reciprocal. So we're going to have a mole containing what? 6.002 by 10 to the power 23 what? Atoms. Okay. So now, what are we going to have? So the atoms here will cancel out. Then we have 5 by 10 to the power 20 being divided by what? Being divided by the Avogadro's constant. What are you getting after doing your calculations? So after computations, the answer that I'm getting is basically 8.303 by 10 to the power negative 4 moles. So these are the number of moles that are contained in what? 5 by 10 to the power 20 copper atoms. That is how you get to look at this question. So we've determined the number of moles. So now looking at the question itself, we only have 3 significant figures. So we need to make sure that even the answer we present should have what? 3 significant figures. So it's fine presenting a solution like that. Going back to our second question, how many more are in that mass of oxygen atom sample? So we've been given the mass. So we also know that the number of moles is basically given as mass divided by what? The molar mass. We can also use dimension analysis to present that. So what do we have? We have a mass of 0.2512 grams. So we want to determine what? We want to determine our moles. So we know that our molar mass, the units are grams per mole. So since we want to find the mole, we need to make it the reciprocal so that we multiply by mole over a gram. So now for an oxygen atom, if you check your periodic table, basically we have 15.994. So 15.9994 grams per mole. So we make it the reciprocal so that we have a mole over what? 15.994. So this is basically getting to match up with what we have. It's matching up with what we have in the formula there, meaning that you get to divide by the value representing the molar mass. Okay. So now the grams will cancel out. 0.2512 divided by 15.994. I'm getting the value that I'm getting is basically 1.57. So how many significant figures do we have? We have 4. So we have 1.570 by 10 to the power negative 2 moles. If you want, you can also write it as 0.01570 moles. Let's move to C. C says a given acid at a concentration of that, calculate the moles in the 25 cubic centimeters of that. So we've been given 0.033 moles per liter. We are asked to determine the number of moles. So if we are to determine the number of moles, we need to make sure that the liter that is on the bottom should cancel out, so that we just remain with what? A mole there. How do we get to do that? So we want to convert the given volume, which is 25 cubic centimeters. It's supposed to be converted to liters. So we know that per every cubic centimeter, there's what? There's a liter. So every 1,000 cubic centimeters, there's a liter. So that if we divide the 1,000 into the 25, we're going to have what? Liters. So cubic centimeters will cancel out. The liter will also cancel out. So we have 25 being divided by 1,000 multiplied by 0.033. I have 0.00825. So this is an exact answer. No need of you rounding it off. 0.00825. The units are what? Moles. Okay, so that's very, very basic, very easy to follow up. Just understand that basically 1 liter, which is also equivalent to decimeter cubed, is basically equivalent to what? To 1,000 cubic centimeters. Then you also need to understand that 1 cubic meter is equivalent to 1,000 liters, or 1,000 what? Decimeter cubed. Then 1 cubic meter is equivalent to 1,000,000 what? Cubic centimeters. Okay, so that's what you need to understand in terms of volume. Looking at D, calculate the number of moles of zinc metal. So we've been given the mass there. So the mass is 22.5 grams. What should we multiply with? We need to multiply by what? The molar mass. Of course, as it's reciprocal, so that we can have grams per mole. So if you check zinc on the periodic table, the molar mass is basically 65. 65.409 grams per mole. So we want to find the number of moles, so we have to make it as reciprocal. So we have a mole on top being divided by what? 65.409 grams. Okay, so this is more like we're just dividing 22.5 divided by 65.409. Okay, so I'm getting 0.34. How many significant figures do we have? We have 3 significant figures. So I'm going to have 0.344 moles. So we've answered this question. So this basically, we're just focused on the issue of you determining the number of moles. And in summary, what we've said is your number of moles is basically going to be determined as what? Mass over what? Molar mass. That is the basic idea there. That's what you need to understand. Okay, moving to the second question. Carbon has 2 naturally occurring isotopes, carbon-12 with an abundance of 98.93% and carbon-13 with an abundance of just a 1.07%. Of course, we do have carbon-14, which is basically has got a percentage abundance of less than 0.01, which is negligible and no need of us showing it. So we are told to calculate the relative atomic mass of carbon. So the relative atomic mass is basically going to be given as using this formula. Okay. So it is going to go by the atomic mass that you have, okay, or the molar mass that you have. So for carbon 12, that is where we're going to put the 12. Then the F in this case denotes the abundance in percentage. So for the first one, we have 12 carbon 12. The percentage is what? 98.93 over 100. Plus, the other one is carbon 13 with a percentage of 1.07 over 100, right? So grab your calculator there and determine the relative atomic mass. So 98.93 divided by 100 multiplied by the 12, I'm getting 11.8716 plus 1.07 divided by 100 multiplied by 13. I'm getting a 0.1391. Okay, so after doing our calculations here, what are we going to have as our relative atomic mass? So we need to add the two. 11.8716 plus 0.1391. I'm getting 12.0107. Okay. So basically this is what we have as the relative atomic mass. And the units that we can work with is what? We can say, we can either put atomic mass units or we can just put grams per mole. Okay. So we've determined the relative atomic mass of carbon. And that's why if you check your periodic table, this is the figure that you're going to see. 12.0107. Okay. We are on the third question now. Feel free to pause the video and try it out. I hope you had enough time to pause the video and tried it out. So copper has a relative atomic mass of 63.546 and consists of copper 63 and copper 65 isotopes whose isotopic masses are that and that respectively. Calculate the percentage abundance of each isotope in nature. So I'll read the question again. Copper has a relative atomic mass of that and consists of copper 63 and copper 65. So now this question is basically very, very simple. It's like they've already given us a relative atomic mass, and from the previous question we had noticed that the formula is basically the respective atomic mass multiplied by the abundance. Okay. So whenever you have more than 2, the same formula continues there. So we've been given the relative atomic mass to be 63.546. So what is the atomic mass for copper 63? It is 62.9298. The abundance there we don't know, so we can put X to represent it. And remember the percentage is supposed to be shared. Okay, so we'll consider, to make our calculations easier, we'll consider the total percentage to be 1, so that if the total is 1, so if one is having a percentage of X, then the other one should be what? Should be 1 minus what? Minus X. So that if you had them, those two give you a 1. If you want, you can also deal with 100. So you say, okay, my total percentage is 100, so one is going to be 100 minus X, then the other one X. So that if you had them, they'll give you what? They'll give you 100. So the basic idea is, if you add, for example, a 40% being denoted by X, the other percentage is supposed to be 100 minus what? Minus a 40. That's what we're trying to say. So now we're trying to assume we've already divided by 100. So adding a total of a 1. So then the other one is 0.9278. This one is going to be 1 minus the x. Okay. So we can try to find the value of x there. So the value of x that we're going to have multiplied by 100 should be able to give us a percentage for the copper at 63. Copper 65 will be 1 minus x multiplied by 100. Let's try to do our calculations there. So we have 63.546 being equal to, if you multiply that, you remain with 62.9298x. Then if you multiply this by the 1, you have, so I'll consider the 1 by the x. If you multiply it by negative x, it's going to be minus 64.9278x. If you multiply this by the 1, it's still going to be a positive value, but I'll write it. So plus 64.9278. But this one is supposed to go the other side there, so that we try to simplify it. Hello? Yes, I've received. Thank you. Okay, let's continue. So what do we have now? So we have 63.546 subtract 64.9278. That's what we have on our left. Then on the right, we had like terms collected already there. So 62 that, subtract that. So 62.9298 minus 64.9278. So I'm getting a value of negative 1.998x. Okay. What do we need to do there? Subtract what is on the left. 63.546 minus 64.9278. We have a negative 1.3818 being equal to negative 1.998x. So divide that 1.998. The value of x that I'm getting is basically 0.69. Okay, 0.692. So we found the value of what? We found the value of x. And if you can remember the formula that we had said for the copper 63, it was we had attached 62.9298. We had attached an x there. Then the other part we had attached what? We had attached a value of x minus 1. So the percentage abundance for the first one, having x, is supposed to be multiplied by 100, which is going to give us what? It's going to be, so copper 63 has got a percentage abundance, multiply this by 100. It's going to be 69.2%. Okay. So 69.2%. Then the other one is going to be 100 minus what? So what basically are you getting there? 69.2 subtract from 100. 100 minus 69.2. We have a percentage abundance of what? For copper 65, 30.8%. So that's how you get to do your calculations with the issue of percentage abundance of the isotopes. So the same formula applies whether they ask you to determine the percentage or they ask you to determine the relative atomic mass itself. Question 4. Determine the mass of each of the following. So how do we get to determine the mass there? So basically we do understand the number of moles are basically given as what? Mass over what? A molar mass. That's what we do have. But then we're also interested in the mass. So the mass is therefore going to be a product of the number of moles multiplied by the molar mass. Okay, so what do we have for our number of moles for the first part of the question? We have 10.2 moles. We need to multiply by the molar mass. So for our molar mass, what do we have? So for molar mass, let's do our calculations. That is the formula that we have. So if you check your periodic table, we have got 2 atoms of carbon. What is the molar mass on the periodic table? It's 12.0107. I'm hoping you do have your periodic table with you. Then for hydrogen, we have 1.008 there. So let's get to add the two. 6 multiplied by 1.008 plus 2 multiplied by 12.0107. The answer I'm getting is basically 30.0694. That is a gram per mole. Okay. So I hope that's what you are getting as well. So now at that point, we are clearly able to see that the moles will cancel out. Then what is going to stand out to be what? Will be the moles. So the answer I'm getting is 306.7 grams. So that is the mass that we have in that question. Looking at the second part, for B, we have been given 1.6 by 10 to the power negative 3 moles. Then the compound that we have is sodium what? Sulfate. So pause the video and try out determining the relative molecular mass of sodium sulfate. So we have got 2 sodium atoms. Each sodium atom has got 22.98977. Okay. So basically, so this is what we have. So what are we going to have in terms of our calculations? So let's get to add the sulfur. We only have a single sulfur atom. So for a sulfur atom, we have got a molar mass of 32.065 plus we have 4 atoms of oxygen, each having 15.994. Grab your calculator there and do your computations so that you see what you're going to have. So 2 multiplied by 22.98977 plus 32.065 plus 4 multiplied by 15.994. So what I'm getting is basically 142.04214 grams per mole. So we have our relative molecular mass for that compound. And in the question we've been given the number of moles. So let's get to multiply. 1.6 by 10 to the power negative 3 moles multiplied by, so what do we have? We have 142. So we have 142.04214 grams per mole. So the moles will cancel out. Do your calculations well. That's multiplied by 1.6 by 10 to the power negative what? Negative 3. The value that I'm getting for the mass is basically 0.22727 grams. So now we'll round out this off to 2 significant figures, giving us a value of 0.23 grams. That is how you get to answer your question 4 there. Question 5. A compound contains only carbon, oxygen, and hydrogen. Combustion of 1.5 grams of this compound gives us what? It gets to give us 2.02 grams of carbon dioxide and 0.9 grams of water. So basically there is a video that I worked on combustion analysis, and if you want to understand more, make sure you get to watch it. Okay, so combustion analysis basically involves you burning a compound of a known formula but of known composition. So we do know that it is made up of carbon, hydrogen and oxygen, but we don't know the empirical formula or in the ratio in which they are. So this is supposed to be burnt or combusted in excess what? Oxygen to give us carbon dioxide and what? And water. This is what we call combustion analysis. So basically we've been given the mass of carbon dioxide and also the mass of water. So using the ratios, if you look at carbon dioxide, in carbon dioxide you have a single what? Carbon atom. So come up with a ratio there. So what is the molar mass of carbon? The molar mass of carbon is basically 12.017, okay, over the total relative molecular mass of a compound. So you are going to have a summation of 12.0107 for the carbon plus 2 multiplied by 15.994 for the oxygen. So you've come up with the ratio of carbon to the compound molar mass multiplied by the mass there. So our calculations there are going to give us the mass of what? The mass of carbon content. So do your calculations down. 12.0107 plus 2 multiplied by 15.994. So what we have is basically, I'll write that 12.0107 over 44.0095. So what is the addition of what is on the bottom there? Multiplied by 2.02 grams. So we see what we're going to have. So what mass of carbon are you going to have? I'm getting a mass of 0.5513. So that's the mass of our carbon there. So for hydrogen, we'll do the same. We'll look at our water molecule there. So we have 2 hydrogen atoms in the water molecule. So that should be multiplied by the mass of water given. Okay. So now we have 2 multiplied by 1.008, which is the molar mass of hydrogen, divided by the total molar mass of water. So that should be multiplied by what? 0.9. So approximately what we're going to have is a tube. So we have 2.016 over, so 2 by 1.008 is given us what? Plus 15.99. So 15.994. We have 18.0154 multiplied by 0.9. So if you multiply that, 2.016 divided by 18 multiplied by 0.9. So what am I getting? So for my hydrogen, the mass that I'm getting is 0.1007. Okay. So we've determined the mass of carbon and hydrogen. So for our oxygen, what are we going to use? Are we going to use for carbon dioxide or water? So you need to know that basically for oxygen, you don't get to use any of the two. You have to look at the compound itself, because the oxygen, we have the excess in oxygen there, which may make up our carbon dioxide and our water there. So we don't want to say no, this and that, but then we're just supposed to look at the masses. So since we have a mass of carbon and hydrogen, and we've been given the total mass of the compound to be 1.5, grams. We can add the 2 and subtract from the total. The remainder is going to represent what? For oxygen, since we are told the compound only contained carbon, hydrogen, and what? And oxygen. Okay. So the total was 1.5. So if we get to add the 2, 0.5513 plus 0.1007, subtract that from the 1.5. So 1.5 minus what? 0.652. I'm getting a mass of 0.848. So that is what is going to denote our oxygen. So we have carbon, hydrogen, then now our oxygen, which is basically 0.848 grams. So we have the masses of the 3 atoms. We need to determine the number of moles by dividing by the molar mass. Okay, so the molar mass here is 1.008. There it is 15.994. So grab your calculator and determine the number of moles. So I'll start with the oxygen. Okay, so to 4 significant figures have 0.05300 moles. For my hydrogen, 0.1007 divided by 1.008. I have 0.099990 moles. Then finally for the carbon, 0.5513 divided by 12.01. I have 0.0590. So we have our number of moles for carbon, hydrogen, and oxygen. So at this stage we can divide by the least number of moles, which is 0.0590. So we divide okay, so we are dividing now by the least number of what? Moles. So starting with the first part, we're going to have a 1 for carbon. For hydrogen, to 2 significant figures, if you get to divide that, you will find a 2.2. For oxygen, basically to 2 significant figures, I have a 1.2. Okay. At this stage, what can we do now? So we can't just say we have a ratio of CH2 or no. We have to do something about it. What can we do? We can multiply by a 10. So we have a 10, 22, and a 12. The highest common factor is what? A 5. So we have a 2. Then now we have 11. Then we have a 6. So that gives us the ratio that we are in need of. So we can therefore say we have C2, H11, or 6. So that is our empirical formula for this kind of equation. Question 6. A solution of 100 milliliters of 0.200 moles per liter sodium carbonate and 200 milliliters of that calcium nitrate solution are mixed together according to the reaction that. The first question says calculate the mass of calcium carbonate that could precipitate. What is the concentration of sodium nitrate solution that will be produced? Okay, so now here is a reaction that we have. We have sodium carbonate reacting with calcium nitrate to give us calcium carbonate and sodium nitrate. Okay, what are we trying to say? What information have we been given? So we've been told a solution of 100 milliliters of sodium carbonate. So here we have 100 milliliters of it. Then we also have its concentration to be 0.2 molar concentration. For calcium carbonate, for calcium nitrate, sorry, we have 200 milliliters, and then we have a concentration of 0.1 molar concentration. Okay, calculate the mass of calcium carbonate. How do you get to determine the mass of a calcium carbonate that will precipitate? Okay, so let's get to determine the number of moles first of all that we are reacting. And for your own information, these are reacting in the ratio of 1 to 1, as you can see from our balanced chemical equation there. Okay, so now let's try to determine the number of moles for sodium carbonate. So molar concentration is mole per liter, so we'd want to convert the milliliters to liters by just dividing by 1,000. So 100 divided by 1,000, what you're going to have is what? Is 0.1. So for our number of moles, which is given as a product of concentration and volume, we're going to have 0.2 multiplied by 0.1. Then the other parts we're going to have 0.1 being multiplied by 0.2. So 0.1 multiplied by 0.2, 0.02. For the other one, I'm also getting 0.02. And since these are in the ratio of 1 to 1, there is no limiting reagent. They are all going to react completely. So you can use any of the two to come up with what? To do your calculations. So we have 0.02 more. Then we have 0.02 what? More. Okay, the first question says calculate the mass of calcium carbonate that would precipitate. Calcium carbonate is there. So you can get any of the two since we don't have a limiting reagent. So I can get calcium nitrate. These are in the ratio of 1 to 1. So the same number of moles that we have for the calcium nitrate is equivalent to the number of moles that we have for what? For the calcium carbonate. So what would just be required of us is to determine the molar mass of what? Calcium carbonate, then we'll be able to find the mass. So I believe we do understand, or we know it's very common. The molar mass of calcium carbonate is very, very common. It's 100.01 grams per mole. Okay, for your own information, you can try it out. Calcium is 40.078. Then carbon is 12.0107 plus 3 oxygen atoms. So it's 100.07. That's what I'm getting. 100.07 as the molar mass of what? Molar mass of calcium carbonate. So we have our number of moles and the molar mass. So the mass is basically given as a product of the two. 0.02 mole multiplied by 100.07 grams per mole. So the moles will cancel out. That multiplied by 0.02, I'm getting a value of 2.00. 2.00. So look at the given information in the question. They are having a least number of significant figures. How many have they? Okay, so we can consider just 2.001 grams. That's what we have for the calcium carbonate as the mass that was produced, or that would precipitate. Then moving on to the other question, which says what is the concentration of the sodium nitrate solution that will be produced? So these now are in the ratio of, you can get any of them. They are in the ratio of what? They are in the ratio of 1 to 1. Okay. So they are in the ratio of 1 to 1. So if it's not in the ratio of 1 to 1, sorry, in the ratio of 1 to 2. So finding the value of x here would require us to multiply. So since here we have 0.02, they are supposed to be doubled. So there our value of x is supposed to be 0.04. Those are the number of moles of the sodium nitrate. So now we've determined the number of moles for sodium nitrate using the mole ratios. Then what was the total volume that we had after combining the two? We had combined 100 plus a 200, giving us what? A 300 milliliters, which is equivalent to 300 divided by 1000. It's going to be what? 0.3 liters. So using the number of moles and the volume, we're able to find the concentration. So concentration is going to be the number of moles dissolved in a given volume of a solution. So 0.04 divided by 0.3 liters mole. 0.04 divided by 0.3. I'm getting a value of 0.1333 molar concentration, or mole per liter. That's how you get to approach that question. Question 7. Silver reacts with hydrogen sulfide gas and oxygen according to the reaction that how many grams of silver sulfide are formed when 1.09 grams of silver reacts with 0.280 grams of hydrogen sulfide and that mass of oxygen. So I'll write the reaction. We have silver reacting with what? Reacts with the hydrogen sulfide and then reacts with the oxygen to give us what? Silver sulfide and water. Okay, so let's write the given information. According to the question, we are taught how many grams of silver sulfide are formed. Grams of silver sulfide. So this is what we're trying to find, the mass. What have we been taught? We've been told we had a 1.09 grams of what? Silver reacting with 0.280 grams of hydrogen sulfide and 0.160 grams of what? Of oxygen. So before we get to do anything here, we would want to determine first of all the number of moles for the reactant cell. Okay, so what we get to do for us to do that? So divide by their molar masses and their relative molecular masses respectively. So look at the formula of silver. Go to periodic table. Silver, which is your Ag there, if you check your periodic table, it has got a molar mass of 107.8682. Then for the hydrogen sulfide, it is going to involve us adding for the sulfur, which is 32.0. So for the sulfide, for hydrogen it's that. Then for the sulfur it's 32.065. Gets to your calculations well. Plus 2 multiplied by 1.008. So I'm getting a 34.081. Then for the oxygen, 15.994 multiplied by 2. We have 31.9988. So what number of moles do we have? I'll start with for silver, 1.9 divided by 107.8682. I have 0.0176. For the middle part, the hydrogen sulfide, 0.280 divided by 34.081. I'm getting a 0.008216. For the oxygen, 0.1609 divided by 31.9986. I'm getting 0.005028. So how do you get to determine now the limiting reagent in this case? How do you get to determine the limiting reagent? So I can pick any number of moles of my choice. Okay. In this case, I'll pick the middle part for the hydrogen sulfate. So I'll first of all start by comparing it to what? I'll start comparing it first of all with the silver. They're in the ratio of what? 4:2. So now, if you have this number of moles, assuming you don't know the number of moles for the silver, how many would be required? So I'll put X to denote the value down there. So if you cross and multiply, 0.008216 multiplied by a 4 divided by a 2. So the value that I'm getting, the number of moles required by that number of moles, is 0.016432. So now the question is, in the question, what did we have? We had that 0.17. So if we had 0.017 and what is required is actually less, so the silver was actually what? The silver was actually in excess, so it can't be the limiting reagent. So this one doesn't qualify to be the limiting reagent. We'll use the same one now comparing to the oxygen. They are in the ratio of 2:1. What are we going to have? So assume we don't know there. Cross and multiply. So we're supposed to divide by 2 what we have. 0.008216 divided by 2. The number of moles of oxygen required is basically 0.004108. What did we have in the question? What we had in the question basically we had 0.005, meaning that we had more of it. It was more than enough than required by the hydrogen sulfide. So therefore, the hydrogen sulfide seems to be not enough. It was limiting because it required less of the available moles of these other reactants. So it would finish faster as compared to the other reactants. And if you try to compare the silver, compare it with your oxygen, they are in the ratio of 4:1. So it's 0.01761 what you have divided by a 4. What would be needed is what? It would require less as well. What would be required would be 0.004, which is still less. So oxygen was more than enough. Okay. But the overall limiting reagent of the hydrogen sulfide. So we're going to use it with our calculations. So how many grams of sulfur sulfide are formed? So they are in the ratio of what? The hydrogen sulfide is in the ratio of 1:1, since 2:2. So they are in the ratio of 1:1. The exact number of moles that we have for the hydrogen sulfide is supposed to match up with the number of moles that we're going to have for the silver sulfide. So we have our number of moles for the hydrogen sulfide. We need to find the mass that was produced. So we have to first of all look at what? We have to look at the molar mass. So go to a periodic table. What is the molar mass of the silver sulfide, which is Ag2S? So for our silver, we have 107.8682. These are 2. Plus, for sulfur, what do we have for sulfur? we have 32.065. 2 multiplied by 107.8682 plus 32.065. I'm getting a molar mass of 247.8014 as what? As our molar mass there. So we have our number of moles and the molar mass. What are we going to have for our mass being produced? So our mass being produced is going to be a product of the number of moles and the molar mass. So after I multiply what we have there, what are we going to have? Multiply by 0.008216. I'm getting a mass of 2.04. Okay, 2.04 grams of what? Silver sulfate was produced. Question 8. Ammonium nitrate is produced when ammonia is combined with concentrated nitric acid, as shown in the following balanced equation. In an experiment, 404.2 grams of ammonium nitrate is produced when 112.5 grams of ammonia and excess nitric acid are combined. So the good part about this question is it's very easy because they've already given you the excess reagent. So the nitric acid was in excess. So the limiting reagent is what? Ammonia. So we get to use what? We get to use the ammonia to determine what? To determine what was produced. So I write the equation. We have NH3 plus the nitric acid giving us ammonium nitrate. So 404.2 grams ammonium nitrate is produced. So that is what? That is basically the given actual yield. That is the actual. So we need to do our calculations using our stoichiometry, which we call the theory or the theoretical yields. So what have we been taught? So we have 112.5 grams of ammonia reacting. So the limiting reagent basically is very important for our calculations. So let's get to determine its number of moles and use the mole ratios for us to determine now how much of the sodium nitrate, or basically the ammonium nitrate, is expected to be produced. Okay, so let's get to have our molar mass of NH3. If you go to the periodic table, you have 1.008 for hydrogen. Your nitrogen, you have 14.00674. 3 multiplied by 1.008 plus 14.00674. If you get to add the two, what I'm having is 17.03074 grams per mole. So before I even get to do my calculations, I would want to determine the molar mass of the ammonium nitrate in advance as well. So for ammonium nitrate, we have NH4, then NO3. So for nitrogen, we have 14.00674. For our hydrogen, we have 4 times 1.008. Then for nitrogen again, we have 14.00674. Then basically we have 3 multiplied by 15.994 for the oxygen. So what happens if we get to add that? So we will have 3 multiplied by 15.994 plus, so we have 2 of the nitrogen there, so I'll say 2 multiplied by 14.00674 plus 4 multiplied by 1.008. Okay, so what are you getting after doing your calculations here? So after doing my calculations, for the ammonium nitrate, I'm getting a molar mass of basically 80.04368. So now, we have determined the number of the molar mass of the ammonia there. Let's get to find the number of moles. So number of moles is given as a product, or rather dividing the mass by the molar mass. So for number of moles, our mass we had 112.5. So we need to divide by that, by the 17.03074. So 112.5 divided by 17.03074. I'm getting a 6.6057 moles of ammonia reacting in that reaction. So now this number of moles basically are the remitting. This is what was remitting. So they are in the ratio of 1 to 1 with the product. So that also tells us to say that that is also the number of moles of what? That is also the number of moles of the sodium nitrate in the reaction. So we need to find now the mass. So since we have the molar mass of the product already, and we also have the number of moles, we can find the mass. So mass is going to be a product of the two. So the 6.6057 multiplied by the 80.0438. So I'm getting a value of 528.7 grams produced. So now what we've calculated is what we call the theoretical yield. It is determined from the calculations stoichiometrically, using the stoichiometric calculations. So now the percentage yield, you get to compare the actual yield with the theoretical yields multiplied by 100. The actual in the question was given to be 404.2. Theoretically, we've calculated we expect 528.7 to be produced. So 404.2 divided by 528.7 multiplied by 100. The percentage yield, what I'm basically getting, is a value of 76.45%. So this is basically the percentage yield of that product in this reaction. In our last question, we are asked to balance the redox reaction in basic media. So if you are looking for a video basically to help you understand this better, check out the video that I made on the balancing chemical equations using the ion electron method. So let's get to do it. So it requires, the first step is basically you are required to split the equation into the half reactions. So half reactions look at what is identical. So on the reactants I have that, and it is more related to that one. So that is my first half reaction, 3 plus, giving me what? O42 minus. From there, the other half reaction involves this. Write it. Then giving us what? Water. So whenever you're dealing with your balancing your chemical equations, the first thing that you need to do is, first of all, you need to balance the atoms. So you get to start first of all by balancing the other atoms before oxygen and what? And hydrogen. First of all, focus on the other atoms. Balance all the atoms. So in this case, we can clearly see that we only have chromium as the other atom other than oxygen and what? Hydrogen, which is already balanced. Okay, well and good. So now, after you've balanced all the other atoms, the second step is to balance oxygen. So you get to balance oxygen by adding what? Balance oxygen by adding water molecules. The water molecules should be in respect to the number of oxygen atoms that are missing on either the left or the right hand side. Therefore, if I look at my first half reaction there, I'm clearly able to notice that I've got 4 oxygen atoms on my right, then on the left I don't have any. So what can I do? Let me even write it in between. So we have chromium 3 plus giving us. So we have 4 oxygen atoms on the right hand side. So we are supposed to add 4 water molecules. So we've balanced the oxygen atoms in the first equation. Now, from there now, after balancing oxygen, you get to balance what? You need to balance the hydrogen. So on the left, we have 8 hydrogen atoms. So we're supposed to add 8 of them on the right. So we've balanced in the first half reaction is balanced. We have an equal number of chromium atoms, an equal number of oxygen atoms, and also an equal number of what? Hydrogen atoms. Looking at the second one, we can clearly see that basically we've almost done the calculations here. Look at that and that. The hydrogen already, they are not balanced. Basically, let's try to focus more on the oxygen for now. So are we balanced with our oxygen there? Are we done? Of course not. Here we have 3 on the left. On the right, we just have a single one. So we can just put a 3 there. We've now balanced the oxygen atoms. But if we balanced the nitrogen the hydrogen atoms, on the left you have 2 plus 1 there, giving us a 3. Then a 3 by 2 on the right hand side gives us 6. So we have 3 shortage there, so we can add them. We have 3 hydrogen atoms missing. So that they also become what? So that on the left hand side we also have 6 now, with 3 oxygen atoms as well. So we've balanced now. We've balanced all the atoms. So apart from balancing the atoms, the other thing that we need to balance is we need to make sure that we have balanced the charges. So on the left hand side, I'll start with the first half reaction. What is the charge? For water it's a 0. For the chromium we have a 3. Then on the right hand side, the charge is a 2 minus and 8 positives. So we have a 2 minus and 8 positives. So a negative 2 plus 8. I have a charge of a positive 6. So you're looking at that. If you get to look at that, you're going to see that we are actually, it's an oxidation reaction. Okay. 3 to 6. 3 to 6 means that what have we done? There's a loss of what? There's a loss of electrons there, which is an oxidation reaction. So loss of electrons is supposed to be shown on the right hand side. So let's get to do that. So we have what? We have 3 electrons being lost in the first reaction. Then in the second reaction, we have 3 positives and a single negative, giving us what? A 2. On the right hand side, we just have water, which doesn't have a charge. So we have 2. So 2 to 0, what does it mean? It means that it was a reduction reaction, which had involved gain of what? 2 electrons. So add 2 electrons to the left. So plus 2 electrons. So before you get to combine the 2 half reactions, you need to make sure that the number of electrons being lost by one reaction should be equivalent to the number of electrons being gained by another reaction. So this is a redox reaction. So the first one we have got 3 electrons, in the second one we have 2 electrons. So I can multiply the first equation by 2, then the second equation by 3, so that we get to balance. So the 4 multiplied by the 2 are going to give us 8. The chromium, which is having a 1, multiplied by 2, it's going to be a 2. That is going to be a 2, then the 8 will become a 16. Electrons will become 6. So after multiplying by 3, 3 by 3 there is a 9. Here we have a 3, 3, we have a 9 there. So we have 6 for the electrons. So now the electrons are going to cancel out. So now at this stage we can now combine the first half reaction and the second half reaction. And what are we going to have? So we have 8 water molecules plus 2 chromium ions plus what? Plus 9 hydrogen atoms plus 3 H2O2 and 3 hydroxide ions. Then on the right we have that. We have 16 hydrogen ions and 9 water molecules. So at this stage now, what we can do is try to cancel out what is common. The spectators, what is part of the left and the right hand side. So at least we can see that the water molecules, we have 8 on the left, which we can cancel, so that we remain with a single water molecule on the right hand side. Then for the hydrogen ions, we have 16, we have 9. So 16 minus 9 will remain with 7 of them on the right hand side. Then what else is common? So these are the common things. So what is going to remain is we have that on the left with 3 H2O2 and 3 hydroxide ions, giving us what? On the right hand side we have 2 chromium that plus 7 hydrogen ions plus water. So in basic media, basically what we just want to see is hydroxide ions. We don't want to see hydrogen ions. In acidic media, we get to see the hydrogen ions. So let's do away with the hydrogen ions by adding an equivalent number of what? Hydroxide ions, so that they form water. So whatever you do to the left should be done to the right, to the left, to the right hand side as well. So here we have that plus 3 H2O2 plus 10 hydroxide ions, giving us what? So 7 hydrogen ions plus 7 hydroxide ions will give us what? 14 water molecules. Or sorry, 7 hydrogen ions plus 7 hydroxide ions will just give us 7 water molecules. So 7 plus the one that is there will give us 8. So we have 2 chromium O4, 2 minus, plus what? Plus 8 water molecules. So do you have anything that is common here at this stage? Do we have anything that is common? There is nothing. So we need to make sure that the charge is balanced. So we have a 3 positive there by 2, giving us 6. Then we have a minus 10 there. So 6 positives minus 10 will give us what? We have a negative 4. On the right hand side, we just have 2 multiplied by the negative 2, which is also a minus 4. So the charges are balanced on the left and the right hand sides. Then the atoms, they should also be balanced. So if you check for chromium on the left, what do we have? We have 2. There we also have 2. Oxygen atoms, 3 by 2 giving us 6. 10 by 1 giving us 10, so 16. On the right hand side we have 2 multiplied by 4, which is 8 plus the 8 down, giving us 16. For the hydrogen here we have 6, there we have 10, 16. So we have 8 by 2, 16. So we can clearly see that the charge and also the atoms are balanced in the final equation. And this is in basic media because we can clearly see that only hydroxide ions are present. So that is how you get to balance. In acidic media, you have to have what? The hydrogen ions. So thank you very much for watching to the end.